All right. So with that, I'm really delighted to for our speaker today, Sam Stanwyck, who is the Director of Quantum Product at NVIDIA. And with that, Sam, I am going to hand it over to you.
All right, thank you, Adnan, and thank you, NJ, and thank you everyone for coming. It's a pleasure to be here. Let me go ahead and share my screen and get started. All right, so hopefully everyone can see that. As Adnan said, I work on the quantum computing team at NVIDIA, and today I'm going to talk about our perspective on quantum computing, where we are today and where we'd like to get to, how quantum computing both integrates with and benefits from other computing technologies and HPC and AI, and then, of course, NVIDIA's strategy and what we're doing to help make quantum computing as successful as possible, as soon as possible. So I wanted to start with a question I get asked a lot, which is why NVIDIA is working on quantum computing and why we're working on quantum computing without building our own quantum processor, which is what Google is doing an amazing job at and what many other companies are doing. And the answer is that really we see quantum computing as core to NVIDIA's DNA and what we can be great at and help enable. And so people mostly know NVIDIA now as an AI company. Before that, it was a gaming company or a GPU company. And none of that is quite correct. NVIDIA is an accelerated computing company. And so we are always looking to expand the frontier of problems that computers can solve and do it as a platform. So not build end-to-end solutions, but build critical technologies that our partners can take advantage of to be more successful. We also want to do that way ahead of time. Part of our strategy is to invest in new accelerated computing technologies far before they are massively commercially valuable. And so NVIDIA released CUDA now over 20 years ago, and CUDA meant that if you knew how to program in C and eventually C++ and Python, you could program a GPU. And this took GPUs from only used for gaming to eventually now where they are today, which is at the heart of nearly every supercomputer. We've been working on deep learning and generative AI for nearly as long, going back to around 2010 when we built cuDNN, a library for accelerating deep neural networks, worked with the team that did AlexNet, and worked with Google, of course, and companies like OpenAI far before the ChatGPT moment. And so we see our role in the industry as investing in these technologies well ahead of massive commercial value and understanding problems that we can solve that are maybe hard for others to solve and that benefit everyone else. And quantum computing is just squarely in that wheelhouse. This is a technology that promises to not replace GPUs and CPUs and TPUs, but integrate with them, complement them, and expand the space of problems that computers can solve to some very interesting problems. We are not at commercial value from quantum computing yet, but we are excited about it both in the near term and as a long-term bet. We also see lots of great companies doing an incredible job building quantum computing hardware. And so we don't want to do that. What we want to do is leverage the things that NVIDIA is great at, GPUs, supercomputers, the software to run those interconnects, thinking about heterogeneous architectures, and build tools and platforms that others can use to make quantum computing more successful. And kind of top of mind here, which should be unsurprising, is AI. AI is transforming how we do just about everything, and that transformation is accelerating really in a quite amazing way. And quantum computing is no different. And when it comes to AI and quantum, it's a bi-directional relationship. So right now, what's happening is AI is advancing quantum computing. We're using AI to optimize quantum algorithms, discover or try to discover new quantum algorithms. We're using AI to solve the inherent problem, the inherent fundamental problem holding back quantum computers from being successful today, which is the noise inherent to quantum bits or qubits through quantum error correction and calibration. And we're using AI to simulate and build models of quantum processors to help us design better ones, understand how they're going to perform, and develop software and algorithms for computers that don't exist yet. So that's digital twins. Looking forward, we are very excited about the prospect of quantum computing to advance AI. So in addition to everything else that it is, a quantum processor is an incredible scientific instrument. It's going to generate completely new types of data. It represents the physical world in a different way. And we expect that quantum processors, in addition to things that people are familiar with, like Shor's algorithm for factoring and, chemistry and materials applications, can integrate with what we're doing in AI and advance AI. So that's, research happening now and a little bit further out. But I just wanted to point out that we see this as a mutually beneficial relationship. And so what does that system look like? We call it quantum GPU supercomputing. And others kind of have different versions of this, but the fundamental point here is the quantum computer is not going to stand on its own. Quantum computers are good for very specific tasks, and we're working to expand that space of tasks, but certainly not good at everything. And so what customers will want is a hybrid system. So CPUs and GPUs and supercomputers as they exist today, augmented by a new type of accelerator, resulting in an overall more powerful supercomputer. And this integration is mutually beneficial. So, as I said in the slide before, quantum computers are going to help us solve new problems and expand the frontier of accelerated computing. But we're also going to need a whole lot of accelerated computing and AI to get the quantum computer to work at all, let alone get the most out of it. So controlling, calibrating, compiling, and correcting errors, the quantum computer is going to benefit from integration with classical computing in many ways. So breaking this down into three pieces that we're working on, kind of starting from the bottom, there's the physical architecture for scaling what are called logical or error-corrected qubits, which are qubits that are free from noise and can be used to solve the problems we're most excited about. That's actually the topic I'm going to spend the least time on, and I'm going to spend the most time on 2 and 3. So 2 is the software to bring this all together, what we can learn from how supercomputers work today and the integration of new accelerators into supercomputing technology. And then, of course, the convergence of AI and quantum. And this is an incredibly hot topic right now. Even when I give a talk 3 months from now, I'm sure what I say today will be out of date. That's true in reverse. So it's an incredibly exciting time for AI and quantum. Oh, and sorry, I'm just realizing you can see my mouse. I'll try to get that out of there. Okay, and we at NVIDIA are not doing this alone. Quite the opposite. So we are already the only AI company that works with every other AI company or close. Our mission in quantum is to be the only quantum company that works with every other quantum company, be that Google or a brand new startup, academic groups, enterprise end users, supercomputing centers. We build our platform in such a way that our partners can take the pieces that they want and leave the rest. And so we're very proud of our partnerships and very proud of this slide. So let's dive into architecture. The ecosystem trend that's really motivating this is the inflection point that's happened in quantum computing in the last couple of years. Google demonstrated the first logical qubit. which is where you use many physical qubits, run error correction, and generate a virtual representation of a qubit with a lower error rate, a better fidelity than the corresponding physical qubits. And this is a process that we need to get to quantum computers that are incredibly valuable. And what's exciting now is this is scaling up. So we are improving both what's called the logical error rate and the numbers of logical qubits we can generate. There are now roadmaps. So these gray dots are from public roadmaps of different QPU builders promising hundreds or thousands of logical qubits over the next few years. And this is the scale where we can start to think about useful molecular and material applications, getting close to broad commercial applications. And so we are now on a ladder climbing an exponential that is very, very exciting. And that's logical qubits. Generating lots of logical qubits needs quantum error correction, and quantum error correction needs different thinking about architecture. If we want to do quantum error correction in a scalable way, the way that we take these errors the quantum system is making and understand them and turn them into the right corrections is a compute-intensive classical process that needs to happen incredibly fast. And so the requirements for this, we think, are here. These are a bit dependent on the type of quantum processor you have. But we consider this at least a publicly unsolved problem today that NVIDIA is in a great position to help with. So we introduced a platform about 6 months ago called NVQLink. And the reason for the name is, if you're familiar with NVLink, the fundamental thing NVLink does is take a GPU supercomputer and make it usable like a single GPU. So it's an interconnect and an architecture to enable that. And NVQLink, while physically the implementation is very, very different than NVLink, it's much more of a platform architecture than an interconnect, but the principle is the same. It makes it possible to treat a GPU supercomputer plus a QPU as a single system. And it solves two problems, which I'm not going to go into in depth, but one is a single interface to any quantum processor. And the second is as much accelerated compute and AI as you need available in real time with low enough latency to do quantum error correction. So NVQLink is in development, but the progress over the last 6 months has been really encouraging. We've demonstrated 3 microsecond round trip latency. We already have dozens of partners from across QPU builders and national labs working with us on this, and a few deployments already. So we're not at the finished NVQLink that leads to fault-tolerant quantum supercomputing with hundreds or thousands of logical qubits, but the QPUs aren't either. And we're confident this is the platform to get us on our way. We had a bunch of news about NVQLink at our GTC conference a couple of weeks ago. So these are all deployments of NVQLink from partners and customers, results on NVQLink. We had a real-time error correction demonstration from Continuum, papers or partner announcements. And so really, really happy with the momentum on NVQLink. I'm going to focus, as I said, more on the software side and more on the AI side in this talk, but I just wanted to highlight the hardware foundational element of our platform. Though we aren't building a quantum processor, we are developing technology to help with the tight integration that's needed for everything that I talk about afterwards to happen. Okay, so let's move on to software. I talked about CUDA a bit at the beginning, and we have a open source quantum analog of CUDA now in the market called CUDA-Q. And the fundamental insight that motivated CUDA-Q is the software that we need to get the most out of quantum computing probably looks a lot like what we needed to get the most out of GPUs. This is a new accelerated computing technology. It's not going to replace what came before it. We'll want to write single source applications that make use of CPU and GPU and QPU. And it's also not the easiest for a non-expert to get into. If you are a chemist or a biologist or an AI researcher and you want to understand how to use a quantum computer today, you do need to go do some work. And each quantum computer is a special snowflake, where you have to basically learn the quantum equivalent of assembly code, and it's different on each one, and understand how to connect it back to your application. And this is of course getting easier with AI, but if we start from the problems that we want to solve rather than how do we build software on top of the physical technology, we're pretty confident that the platform you want is something like CUDA-Q. So CUDA-Q is open source. It extends Python and C++ with quantum kernels. These quantum kernels are compiled down in a hybrid strategy with our classical compiler to an intermediate representation where they can be executed on either physical or simulated quantum processors, because users also want to be able to try something in simulation, then go run on a quantum processor, then go try a different quantum processor without having to rewrite their code. With CUDA-Q, you can do that with just a compiler flag. We're now proud to support both powerful GPU accelerated simulators in Google Cloud and elsewhere, as well as a large ecosystem of physical quantum processors. So the top half of logos here are different types of QPUs we support. They span superconducting, trapped ion, neutral atom, photonics, spin, which otherwise would be very different in terms of how you program them. The bottom half is the platform side of CUDA-Q. So these are companies who are developing software that builds with or builds on top of CUDA-Q. We do not expect this to be the be-all and end-all, just like CUDA is not. But we try to provide valuable pieces that partners can take and integrate. We do have our own library ecosystem. We integrate with our classical CUDA-X library ecosystem and get to take advantage of that developer base, and are now building libraries, quantum libraries on top of CUDA-Q. We provide learning tools to help one get started with CUDA-Q. And of course, this is NVIDIA. We prioritize performance. So that's CUDA-Q. It's part of a platform, just like CUDA is not one thing. CUDA-Q is not one thing. Beneath CUDA-Q, we also offer libraries for accelerated simulations. These are called cuQuantum. cuQuantum is much more like a classic NVIDIA GPU math library. And cuQuantum is integrated with CUDA-Q, but productized separately. And the reason for that is so we can GPU accelerate not just CUDA-Q, but everybody else's framework, or any researcher's simulator. These logos on the right are other quantum computing frameworks. The top left there is Google Circ, and here are many other leading frameworks, all of which have cuQuantum integrations so that their users can get drop-in state-of-the-art NVIDIA GPU accelerated performance. And this is kind of core to our strategy to productize things in a modular way. So you can take CUDA-Q, but if you want to develop your own framework or use your own framework, that's great. We want to plug in and accelerate that too. cuQuantum is incredibly powerful, both for performance and for scale. It has libraries for state vector, tensor network, density matrix, stabilizer for the experts, and more. And one just kind of cool result I want to show is people talk about simulation of quantum computers as being inherently limited in scale. And that is very true. Otherwise, quantum computing wouldn't be interesting if you could just simulate a quantum computer with a GPU. But you can do a lot more than most people think. There's not a hard cap of 40 or 50 qubits on the number of qubits that can be simulated. Depending on your application, if the connectivity is low and the circuit depth is low, you can sometimes simulate hundreds or thousands of qubits using tensor networks or other approaches. And this is not a universal approach, but for particular types of algorithms research people want to do, it's very, very useful. So this demo was scaling up to tens of thousands of qubits on a quantum machine learning application, which is a bit extreme. And this is a single GPU. The point this is meant to illustrate is simulation. We see it as, on one hand, a stopgap before quantum processors are ready, but much more than that. It's a tool for algorithms research and quantum processor design research that is going to persist and complement into the era of useful quantum computing. NVIDIA is still simulating everything we possibly can about our GPUs, 30 years into GPUs being useful. And we expect that to be true for quantum processors as well. On top of CUDA-Q, we have the CUDA-Q libraries. I'm not going to go into this in detail, but these are the quantum analog of the CUDA libraries. So optimized kernels in CUDA-Q for quantum error correction and hybrid algorithms. And at the very bottom, we have NVQLink, which is our reference architecture for low latency integration. This is our whole platform. It all works together, but each piece is also released individually. So you can take any piece or combination of pieces that you like and leave the rest. We also had tons of partner announcements around CUDA-Q recently at GTC. So, I think as I've illustrated, we're really proud of our ecosystem. And this is constantly expanding, and we're always looking for new partnerships and to help our partners and customers succeed with CUDA-Q. So very, very proud of the great results people have shown. I did want to highlight our newest library in CUDA-Q is called CUDA-Q QEC. And just as a product manager, I am incredibly excited about this product. I think it does something that nothing else in the world does today, which is provide a high-performance, comprehensive toolkit for a quantum error correction researcher to do quantum error correction research. And this is incredibly important right now because we don't yet know exactly how to scale QEC. And so with CUDA-Q QEC, you can generate a custom noise model, feed that into a DEM, a detector error model. You can then do two things. You can either run on a GPU accelerated simulator to simulate many, many shots, or you can configure a decoder to run on real hardware. Or you can do both. And if you do both, and you have real hardware available, you can run decoding with real shots on a QPU over NVQLink. And we have a few partners using this now, which I'll highlight with great success. But it's a very, very exciting new library, CUDA-Q QEC. The most interesting result has been from Quantinuum. So Quantinuum is a company in Colorado who builds a quantum processor out of what are called trapped ions. And their QPU has some of the highest, if not the highest, fidelities, which is the lowest error rates. Others have more scale, but it's a top quantum processor. They used an out-of-the-box decoder that we provide in CUDA-Q QEC with an NVQLink integration to a Grace Hopper GPU. And we're able to take that state-of-the-art quantum processor and reduce the error rate by another 5x. So from about 5% to less than 1%. This takes a number of logical operations you can run from 14 to about 70. And they showed that the specs of CUDA-Q QEC and NVQLink were much, much better than they needed. So the mean decoding time was about 30 times faster than required. We need to scale this up. They need to scale this up. But it's a very, very exciting proof that this works in the real world and is making state-of-the-art QPUs better already through our platform. This is also being used for state-of-the-art quantum error correction research. Another result from GTC was from a company called Alice & Bob. They build what are called cat qubits, which are a variation of superconducting qubits like the ones Google builds, with some trade-offs made. And one of the advantages of their trade-offs is that they think they can do more scalable quantum error correction. But to do that, they need to discover completely new codes. The same codes that work for others won't work for them. They got a 10x speed up in their research workflow by dropping in CUDA-Q QEC. We're able to discover and test new types of codes called elevator codes, which may offer a 10,000x lower error rate. So this is research. I'm not gonna overstate the claim here. They're very excited about it. We're very excited that we were able to make this possible. And it's not just error correction. All the way at the other end of the spectrum, we need to think about, I guess, the other end of the stack at the highest level. We need to think about how quantum processors integrate at the user level with supercomputers. And we had some exciting news from Pascal, who make yet another different type of quantum computer built out of neutral atoms, who showed they were able to integrate CUDA-Q with Slurm through a platform they developed called QRMI, Quantum Resource Management Interface, and provide a user experience with a quantum computer that is much more like what your traditional HPC user expects with CUDA-Q. And so again, this is, there's a lot that needs to be developed here, but just wanted to highlight we're kind of working at both ends of the stack. All right, so I will, with that, get to how AI and quantum are converging. And the problem still to solve is really simply illustrated like this. We have amazing quantum processors to get today. The work that's been done to get them to where they are is unbelievable. But we still have a ways to go. They're not used to solve useful problems yet. We want to scale up the number of qubits by a few orders of magnitude. We want to improve the logical error rate by many orders of magnitude. So there's a lot to do. And the good news is, just like AI is accelerating many things that we're doing in science and engineering and technology in unbelievable ways, now it has the potential to do that for quantum. So these are all papers in the last few years of different problems we need to scale quantum computers and to get the most out of them, from error correction to calibration to readout and more. I think a couple of these are actually from the Google team or involved with the Google team, the Google Quantum AI team. And all of these are using AI, and AI is only getting better. Breaking it down into the workloads that we see, we need to develop better algorithms and applications, so we know what to do with a 100,000 or million qubit quantum computer, and so we can pull in the timeline, and we can reduce the requirements. And there's amazing work happening on this now. We need to develop better hardware, so develop the EDA tools for quantum. We want to generate synthetic data to train AI models for quantum, and then use quantum to generate new types of data. We want to correct errors, do quantum error correction in real time. And eventually we want an AI native, fully deployed system. And NVIDIA, we're not building the quantum processor. We are building the classical hardware and the interconnects and the software to enable all of this. And we've tested benchmarks for all of these. This is our Grace Blackwell 200 platform. Not going to go into tons of detail. We have a paper on it that's linked at the bottom, and I can link in the chat if you're interested. But we can have a transformative impact on people's ability to apply AI to quantum. And then last thing I'll touch on is AI for quantum developers. And I think if you're paying attention to the news, or a developer, you're probably exploring agents and hearing about claws and how fast they are improving workflows. That's true for us at NVIDIA, and it's increasingly true for quantum developers. And so these 4 logos are all companies that have come out with agentic platforms for quantum development that all integrate CUDA-Q. This is now a big priority we think about in terms of users. So users are people, and they are now also agents. And this is going to be more and more the case, and it's a really good thing because it's going to accelerate the pace of development. We're in testing now with many partners. QBraid has some fantastic results that are improving month over month using CUDA-Q to run challenging quantum tasks on both simulators and 6 physical QPUs. And so these are agent coders who are now passing some of their hardest tests at an over 80% rate, and we expect that to keep on improving. And yet again, I want to emphasize we're not doing this alone, and we can't do this alone. And as NVIDIA, what we're doing in everything that I just talked about is building the platform or building platforms and products to make everyone else successful. And that's from hardware and software builders to research centers and academia and enterprise and more. So I'll stop there and leave this up. These are links and a QR code to get some access to some of the things I just talked about. CUDA-Q, cuQuantum, the CUDA-Q libraries. I didn't touch on CUDA-Q Academic, but it's actually my recommended way to learn more about CUDA-Q and our platform and get started. And then I also didn't get the chance to touch on NVQLink much, but if you want to read about that, that's in the link at the bottom. So with that, I'll leave this up. Thank you for your attention, and take questions if there are any.
Hi, Sam. I think my system's all back working again here. So can you hear me?
Yes.
Great. All right. So I will ask some of the questions that have been posed in the Q&A channel. And I want to remind people that you can still submit questions in the Q&A feature. It is in the bottom right corner. It's the icon next to the right of the chat window, chat icon. If you click on that, you'll see a list of tools and you'll see a Q&A feature, and you could submit questions there. All right, Sam. So first question we've got. Does NVIDIA's quantum computing research extend to qubit R&D and low-level physical simulation, parentheses, computational electromagnetics, et cetera?
That's a great question. Right now it doesn't directly, but it does through partners. So what we do have is libraries within cuQuantum for things like dynamics and density matrix simulation, for things like solving the Lindblad master equation, and then for more like computational modeling, we're working with Synopsys, Cadence to start offering those, and more to come on this. I hinted at it with Qubit EDA, and I think this is an exciting opportunity of something to build to accelerate the world over the next couple of years.
Great. All right. Another question that came in. I read a ton about vGPUs from NVIDIA. I read a ton about vGPUs from NVIDIA last year and haven't heard much about it. How can virtual GPUs work with emerging HPC or QML tools? So is there a role for vGPUs in this, or is that primarily for other applications and needs?
I am not an expert on vGPUs, and probably not the best person to answer that question.
My hunch on that one, Sam, and I guess we should dig into this, but in general, the horsepower of the GPU is needed for things that you mentioned. The classical side of the computation is doing error correction, et cetera. So whereas vGPUs are a really useful technique, well, and actually, I'm not sure if they mean vGPUs in the sense of slicing the GPUs to get fractional GPUs, or if they merely mean GPUs in a virtualized environment. I assumed the former. If they mean the former, my guess is you're mostly going to need the entirety of the GPUs, and many of them, to perform actions like error correction and things like that. So Sam, maybe you can address that. How computationally intensive, how GPU computationally intensive is it to do things in hybrid classical computing with GPUs? Can you give any rules of thumb for if you're doing this many qubits, you're not only going to need more than one GPU, but you're going to need X number of GPUs per qubit or something?
Right. So for simulation, it scales exponentially in some dimension. So if you're trying to hold the full state in memory, it scales exponentially with the number of qubits. And so for low 30s qubit count, you need one GPU. For 40, you need order 100. For 50, you need the world's largest supercomputer, and then you can't do more. There are other approaches to simulate that I talked about, where the scaling is not for qubit count, but it's similar for number of operations, circuit depth, or entanglement. But that you generally want a lot of GPUs if you're trying to do cutting edge work. Same, obviously, for training AI models for quantum. For quantum error correction, it's real-time quantum error correction on quantum processors today is like one GPU. And the reason for that is the quantum processors today and the codes that we're trying to run are much, much smaller than we expect that we're going to need. If you're trying to do research into development of new quantum error correction codes, then you're getting into simulating the quantum processor again, and the exponential thing applies again. And as quantum processors scale up, right now we're estimating petascale for compute for error correction for our first useful quantum systems. But that has the potential to move by an order of magnitude. The error bar is really large. So long answer, but hope it's helpful.
So Sam, I want to dig into that a little bit here. In theory, a universal quantum system can be a universal computer and can, in theory, solve any kind of problem as a quantum system. Now, we know that these quantum systems, even if they are universal quantum systems, are still going to be hybrid for a variety of reasons. You're not going to depend on a quantum system for things that must be deterministic. You're not going to depend on a quantum system to do things that classical computing can do much more cheaply and efficiently, and so on. So where are you? Can you categorize the roles again? You said it in the presentation, but I want to dig into it. And first, can you re-summarize the roles you see the classical components playing in a hybrid classical quantum system? Error correction obviously being one.
Yeah. So the nice thing is they're almost opposites in terms of strengths. So quantum computers are very, very bad at high data throughput workloads. It's very inefficient to load data onto a quantum computer. It's very inefficient to get data off of a quantum computer.
Mm-hmm.
And there's just a certain set of quantum algorithms where quantum computers are more efficient than the classical computer, and the set where they're more than quadratically efficient, which is what we're really excited about, is even smaller. Those tend to be, well, so factoring is one, but broadly in the space of high precision simulation of nature. Either direct simulation or generation of training data. So the applications are things like drug discovery, material science, better batteries, more efficient ways to generate energy, and so that's where we expect the quantum computer to help. And there, what the classical computer is doing is correcting errors for one, calibrating, including probably in real time, calibrating the quantum computer. So these systems drift over time, and actually Google had an amazing result recently that showed you can use the same data you use to correct errors to adjust parameters in the quantum computer and hopefully keep it running over many hours or many days. So calibrating and then the classical side of hybrid algorithms. So in almost every case, you want to do lots of classical preprocessing to prepare the best kind of initial state or initial guess for the quantum computer to then take over. And then often lots of post-processing techniques like error mitigation to take the output the quantum computer has given you and get something even better. And a lot of algorithms are inherently kind of hybrid and back and forth. And so it's really like the quantum computer is an amazing, highly specialized accelerator. And then the classical computer is like the bulk resource doing everything else to get the most out of it.
Right. So we can probably broadly characterize the role of the classical system into two bins. One, a bin due to the nature of noisy quantum systems now, needing to correct for errors, needing to keep the simulation going by keeping things in line, basically. And the other probably never goes away. The fact that the application probably has algorithmic components that are better suited for the classical side, as well as some that are better suited by the quantum side, that it handles things like serial sections and IO and all of that stuff better. So even long term, as we address the noise and error situation in these quantum systems, these are likely to still be classical hybrid systems, correct?
Yeah, though I'd also say the error correction is never going to go away because of the just what qubits physically are. And, you know, to some degree, the future is unknowable, but, you know, quantum systems are just much more inherently sensitive to error than transistors. And the way that quantum computers operate means that errors accumulate. And so, you know, right now, the very best quantum computers make errors about 1 in 1,000 operations. I would say if you ask most physicists at the cutting edge, they'd say maybe we can get another factor of 10. The most optimistic would be a couple factors of 10. Wow. But that's still 1 in 10 to the 5.
Yeah.
And we want to run billions and trillions of clock cycles. We want 1 in 10 to the 15. And so we're not anticipating a world where error correction goes away even in the long term. What may happen is it gets kind of boxed up and considered just a part of the quantum computer and a thing that's happening as part of the quantum computer and not something the user thinks about. But for the next 5 years, we think that quantum error correction itself is a user-facing application.
Got it. All right, let's see, another question here. Is there a qubit estimator tool similar to the ones that IonQ, Qiskit, or Azure Quantum introduced last year?
We don't have one of those. Those are great and very valuable. We haven't found something yet where we can dramatically improve on what those groups are doing. So recommend using one of those.
All right. We got a question from Merle Ram. It says, I didn't hear much about D-Wave. Is there a particular reason?
There's no particular reason. I just called out a few partners to highlight. D-Wave does use NVIDIA GPUs in their hybrid solver. You know, for those who aren't familiar with D-Wave, this is a different type of model for quantum computing called quantum annealing, which is not a universal quantum computer, not based on a gate model, but interesting for looking at problems in the optimization space. Although an interesting thing about D-Wave is they just purchased a company that builds superconducting qubits, and so they are also very excited about, you know, everything I just talked about. But yeah, no reason in particular they weren't called out.
All right, got a question from Jan Blomart. Hi Sam, thanks for the very interesting overview talk. Is the focus for deploying NVQLink on classical software simulation, or is the focus on deploying in real quantum hardware? And what number of physical and logical qubits are you supporting?
The focus is real quantum hardware. You can use NVQLink in simulation. You can link a GPU simulator pretending to be your quantum computer and your decoder. But the partnerships I showed and the results I showed are with real quantum hardware. The NVQLink is scalable. We expect up to 100,000 or 1 million physical qubits. No one has that now, but for example, it's integrated with Quantinuum's 100 qubit or 98 qubit processor, Helios.
Got it. And another question here. Can all these systems be used and tested for free by anyone? Are there any limitations? So I might rephrase this question for you, Sam. How would people get access to using some of the systems that you mentioned in here in concert with NVIDIA hardware and software?
Well, these links are a great place to start. for all the options. All of our software is freely available. Everything that doesn't directly depend on NVIDIA hardware specifics is open source. There are some things like, our low-level simulation libraries that aren't, but even those are free to use. You can use them through your favorite cloud service provider. We love that, or anywhere else you'd use free open source software.
Great. With that, Sam, I want to thank you again and ask everybody to give a round of applause using the Meetmoji in the bottom of the center of the screen to Sam for that presentation. Sam, thank you so much.